What's up, everyone? Welcome to Bonquisitive Tech Studio. So today we would be doing something new. Let's first start with a small demo and then I'll discuss. Okay. So let me run this code. Yeah. Hopefully you can see now. So what we are watching today is AI trying to play Snake. But here's the twist. It starts as a complete idiot, zero knowledge, just random movements, crashing into the walls, crashing into itself. But by the end, we are trying to evolve this into a super snake that navigates mazes like they have got a brain. And we are doing this with genetic algorithms and neural networks. So one of the very basics of how you can create an artificial brain is through neural networks, and we are basically trying that. No hardcore machine learning libraries. So let's get into it. Okay. So first of all, while it plays, let me try to understand why it's such a hard problem. Snake itself is a very simple game, right? So you have a greed, you have a food, which kind of randomly appears once you kind of solves it once, and the snake has only one mission: don't die, eat the food. But here's the thing. The AI, when you basically want AI to play this, it has to learn three things simultaneously. One, it needs to understand where the walls are, not as abstract concept, but as immediate danger. Two, it needs to know where its own body is, because again, if it basically just runs into or hit itself, it's also game over. And three, it needs to actually find the food. And here's the kicker: the food spawns randomly every single game. So what would happen with traditional programming? So if I want to basically try to program it, it would be basically a very complex if this then that kind of a logic, right? And so there would be uh, so many conditions, pathfinding algorithms, state machine. It would get messy very fast, and it will be very complex as well. But today I am trying something completely different. We are basically going to let evolution figure it out. So we are basically doing something called genetic algorithms. Okay, so let's talk about the architecture, and you can see the architecture over here in the neural network section. This is basically a live neural network activations as well. Let me try to tell you. So these there are 11 input nodes. So here at the leftmost, you can see the input nodes. I have put like 11 neurons. You can say the first three neurons are like danger detection. Like, is there a wall or my body immediately in front, to my left or to my right? Like, if there is in a danger immediately to my front, left, or right or not. So it's like binary: one for danger, zero for clear. Then there are neurons for the current direction, like one hot encoded. So like if moving up or down, the neuron 4 will say, if it's moving up, then the neuron 4 basically fires. Moving down, neuron 5 will trigger, things like that. So 4, 5, 6, 7, they are for four different directions: up, down, left, right. Then 8, 9, 10, 11, this is for food direction. Is the food above me, below me, to my left, or to my right? Again, a binary, right? So again, four neurons for that. Why we are going like this? Because neural networks, so this is basically a perceptron. So you have this input and you have the output. In the output layer, you have three neurons only. Like you can go straight, which is this one, straight. You can turn left or you can turn right. A snake can't go back, right? So it only has these three decisions. So what we're doing, we are basically putting all the inputs in all these neurons. Then these are the output neurons, and then there is a hidden layer, right? The decision is simple: whichever output has basically the highest value while goes through this network, we do that action. No softmax here. But for the hidden layer, which is also by the way configurable, you can see here I have put in the number of hidden nodes as configurable. So there I have put ReLU activation, rectified linear unit. This is where the network learns to combine all that raw input data into what decision it can take, like the ST, like straight, left, or right. So that's basically in the hidden layer only. And you can watch like which green means basically active. So you know like which hidden layers are being active at the point of time of this game is being played. Now here comes the genetic part of it. The genetic part is very important. So you see we have like a population. So how are we gonna make it run? Because it's basically plays and it understands, it tries to learn. Usually machine learning happens like this only, right? You have a lot of data specifically supervised learning. You have input data, you have corresponding output data, and you try to learn the weights. But now we are not actually trying to learn it through that. We are not trying to learn it through any gradient descent or any optimization algorithm. What we are trying is genetic algorithm. What happens in evolution or in genetics, we basically take that. This is a very popular approach in computer science as well. So we start, say for example, we start with a population of 20 completely random neural networks. They have no idea what they're doing. Like it's completely random weights, random biases, and it would crash constantly, right? Most snakes following that neural network, it will die in like two to three steps only. But then natural selection kicks in. We have defined a function. You can see the average fitness. What's average fitness? What we're doing is this is the score that it's doing. Score means like once it kind of eats the food, it's one score, right? The score into 1,000 plus steps taken. So if I write it here, so let me quickly write it here. So we are basically have done fitness, which is nothing but score into 1,000 plus steps taken. And basically what's this? So we are basically measuring this fitness, and score is basically whenever it can eat the food, it's basically one score. And you can see the base score, gen base score. These are the these things, right? So even if it doesn't able to score anything, if it can take some steps means how many steps it can take successfully. It can take some steps, you get points. And this is the fitness function that basically we have done. So every piece of food taken, you get like 1,000 fitness points. Every step survived, you get one fitness point. And why this formula? Why I'm making things like this? Because it creates a dual pressure. The snake wants to eat food, but it also needs to survive long enough to do it. If it just sits still, it will get zero fitness, right? Because again, no movement means nothing. So it won't cover any steps, it won't eat the food, its fitness will be zero. And once it eats one food and dies immediately, gets 1,000 points. But a snake that eats food and also survive for say 100 or 200 steps, then it's almost like 1,200 fitness score from that one food alone. So now what we are doing at each generation, and you can see the generation 8. So after like actually doing all these 20 snakes playing each other, we are basically taking the best performing snakes as the parents, and then what we are trying to do is tournament selection. So we pick parents for the next generation, and we basically take the top 8 performance of the generation, randomly pick 3 of them, return the best of those 3. Now we do a crossover. So it's almost like how even sexual selection or even a generation happens, right? So you take 50% from parent A, 50% from parent B. And what talking about, I'm talking about every single weight in the network. So you have a lot of weights and biases, like those are the parameters of this neural network. We are taking 50% chance. Basically it's like a flipping a coin. You have 50% chance to get the gene from parent A, or 50% chance to get the gene from parent B, mom's brain or dad's brain, right? And basically mixing the weights. So we have these all these parameters, weights and biases. We for all of them we are stochastically taking them from the parents weights. Okay. So for each generation we are doing that. But not only that, we are also adding something important. That's the mutation. You can see there's a mutation rate, which is set to 5% right now, 0.05. So what is mutation? And what is 5? So 5% means like this is basically key to evolution, right? Every generation, once it goes from a parents to child, so it there might be this crossover of the genes from parents to children. The child gets something from mom, something from dad, but again there are some point mutations that can happen which can have some benefit to the reproductive fitness. Here what's happening here, we when it mutates, we add a random value between minus zero point 0.5 to plus zero point 0.5, minus zero point 0.5 to plus zero point 0.5 to a weight. So it's a random mutation that we are doing. We have kept it low. 5% is low, so that like evolution kind of crawls. If it's too high, we might lose some good traits. Okay, it's like learning rate as well, something like we use in gradient descent. If it's too high, you might actually lose the uh, minimum, global minima as well. So we have kept mutation low. Basically 5% seems like a sweet spot, small enough to refine it slightly slowly, but at the same time large enough to explore as well. So as generations increase, you explore a lot, right? And what happens, most weights stay the same. Occasionally one or two, like since it's just 5%, so occasionally some would be changed, and that's basically evolution doing fine tuning, right? And what's happened, the top four snakes in every generation, again we clone them directly to the next generation, untouched, no crossover, no mutation, preserving the base genetic materials that we have found. Okay, so here's the full loop. As I talk, let's basically try to rewind and get the full loop. We generate like 20 random brains. Each brain plays one full game of snake, calculate fitness for that. We create next generation, clone top 4 unchanged, then fill the remaining 16 with offspring from tournament selection, crossover, mutation, those kind of a thing. And then we repeat. We repeat and repeat and repeat. And through this repetition, through generations, what happens is that you kind of keep some things, keep the top performing genes kind of alive, and also do some kind of mutation, some crossovers, so that you basically kind of generate new features, and basically your brain kind of evolves, and you can see the progress history. Obviously sometimes it drains, but at the end it also kind of, it's learning as well, it's learning very slowly. If you see the blue chart, which is basically the average, it kind of very slowly it kind of goes up. And if you also just have looked into the average fitness, this is also going up. And basically what I have seen, and you can basically, by the way, increase the speed of generations as well, speed of all this play game. It automatically just plays and it tries to learn, and it's not through optimization that it learns, it's just through genetic evolution that it tries to learn. And it's a very simple network, simple neural network that I'm using. It's not at all like you guys all use LLMs, which is basically use transformers, encoder, decoder architecture. They are very complex neural networks. This is the simplest neural network that you can have, with input layer, with just one hidden layer, and then there's the output layers. But still, we are basically going slightly ahead at each time, right? We are basically going ahead, and yeah. So as it progresses, you would see sometimes the average fitness goes down, sometimes it goes up. But as the generation progress, sometimes it can go down as well, because again we are not optimizing for just the best, we are just selecting from a single generation, right? Even in biology, sometimes if reproductive fitness basically goes down, sometimes species also get extinct. Not always it's external trauma or external events, natural disaster, that makes them extinct. Sometimes it can be because the features that it inherited, they are not relevant enough to survive in the environment. Anyway, so this is a very cool experiment that I was doing, and I thought like it would be great to show you that. Basically this is just a single HTML file. Again, I use AI, agentic AI to kind of also write some of this for me as well. But yeah, you can just go through the HTML. So pretty straightforward. Most of the stuff is pretty straightforward. How the neurons are basically defined, direction vectors. Then yeah, the genetic algorithm, actually how the evolution would work, how the next generation we will basically how to sort the fitness, how basically we do the population tournament ranking, so and so forth. So very simple enough, like just the HTML itself is not that complex. I'll add this to my repo, GitHub repo, and you can have a look at it. That doesn't okay. Probably that sounds good. So yeah, so this is what I was trying to do. If it, I have seen like after 40, 50 generation, it starts getting good. By the way, I have seen it doing best code of like 9, 10, 11, 9, 10 as well. So yeah, it learns. Obviously, we are basically trying with very simple networks, so it would take some time to the natural selection to get to work, right? So yeah, but hope you learned something. Genetic algorithms are a very interesting thing that a lot of computer scientists use in a lot of kind of problems, complex problems. But yeah, just applying this in a very simple problem. Hope you get to learn something. So bye bye. Take care. Hope you learned something from this. See you soon. Bye.